Okay, guys, I welcome you this afternoon to structural biochemistry. Today we're going to be looking at lipids. Yeah, we're going to do the first part of lipids. Then at the end, we're going to do the TD for glucid, which I sent in the group. And I guess there are certain guys amongst you who are going to help us. Yeah. Okay, we'll proceed. What are lipids? I guess you have heard about lipids. What are lipids?
Lipids are molecules, or let me say macrobiomolecules that are insoluble in water but are soluble in organic solvents.
Okay, correct. Yeah, lipids are a heterogeneous group of organic compounds that are insoluble in water, insoluble in water and soluble in non-polar organic solvent. Lipids are classified into two parts. We've got simple lipids and complex lipid. Before I jump into simple and complex lipid, I could like to talk about the biological law of lipids. As we had looked at in glucid, there are certain biological law of glucids which are similar to lipids. We have got low energetic, low metabolic, and low structural, of which the rows which we looked at in glucids are similar. Who can remember the raw energetic which we looked at in glucids?
I remember that, and in their energetic roles, they act as conservators of energy. When there are not enough glucids in the body, they can be oxidized to give energy. That's what I remember.
Yeah, they act as reserve. In short, this structural. Hello, guys. Who remembers what I talked about on structural?
You can say something. Can you get me?
Yeah, I can get you now.
Okay. It acts as elements of support.
Sorry, I can't get you.
Saying the structural role that we talked about is it acts as an element of support. Yeah, and also reserve in the form of glycogen or starch. Yeah.
You're combined. You're talking about the two things. You're talking about structure and energetic role. Yeah, they act in the protection of the cell, the cellulose. If you remember in the structural protection of the cell. Then we talked about the raw metabolic. What do they say on metabolic law? Guys, we looked at this in. What do you say about metabolic law?
I think that's the part where we synthesize them to form energy.
Okay. Other one? Yeah, okay. As she has stipulated in energetic law, it is used as a reserve. In structural, it is used for protection, protecting the plant's leaves from drying up, protection. Or we can talk about the protection of the cell wall or cell membrane. Then for metabolic law, as she has stipulated, who stipulated it? Who answered for metabolic?
Lillian.
Yeah, as Lillian said. Then we're going to talk about the origin. The origin is the same with what you had looked at. It is both endogen and exogen. What do I mean when I say endogen? Endogen is something which, when endo means inside, exo means outside. So when I talk about exogen, we talk about issues to do with alimentation, food, the food we take. Then when we talk about endogen, we're going to talk about the reactions which happens inside the body to formulate the lipids. Am I clear?
Sorry, may you please repeat that?
The origin of lipids. Lipids have got two origins, which is endogen and exogen, as we had looked at in glucid. Endogen, when you talk about endo, it's something to do inside, the reaction which takes place inside. Then when you talk about exogen, we're talking about something to do outside. Exo is outside. Something to do with the food intake, the food we eat. Is it clear? The lipids are classified into two, like I earlier on stated. We've got simple lipids and complex lipid. Simple lipids. On simple lipids, we have got three types. We have got glycerol, glycid, and steroid. We're going to look at them, each one on its own. We're going to look at these three types of lipids. And these simple lipids are something which are composed of carbon, hydrogen, and oxygen. That's their composition. Then complex lipids These are lipids which are composed of carbon, hydrogen, oxygen, and sulfur and nitrogen. These are biological laws we have talked about: energy, structure, metabolic. Yeah, from what we have looked at, is it clear? From what I've said.
Yes, it is. I didn't get on the biological roles of lipids.
Okay. Biological laws of lipids. Lipids play a major role in biology. There are three main roles which it plays. The first role is role energetic, which act as a reserve. Then we've got structural law, which we talked about the protection of the cells or the cell or the membrane. When we talked, then we also said it also play a role metabolic. A low metabolic, you're going to look at it in detail when you start doing is it metabolic biochemistry. You're going to look at it. That's where you are going to concentrate much on low metabolic. But it's something which deals with the sympathies of hormones in the body. You're going to look at it in detail when you start doing metabolic biochemistry. Is it clear?
Yeah, it is now.
Yeah. Mostly, guys, these lipids, it's something little bit easy from glucid. Lipids needs reading, but yeah. Then we're going to talk about acid gra. What is an acid gra or fat acid? There's somebody, I heard somebody who talked about fat acid. What are fat acid?
Fatty acids end products of the digestion of lipids.
Another one. Let's participate. What are fat acid?
They are part of the constituents in a lipid. More like they are the building blocks of the lipids.
Another one. I want to get 2 points. Another one before I come in. Okay, to save time. Fat acid is simply a carboxyl acid with a long aspartic chain. These are fat acid. Fat acid is simply a carboxyl acid with a long aliphatic chain, which is either saturated or non-saturated. Is it clear?
No, repeat.
First acid. First acid is a carboxylic acid with a long aliphatic chain, which is either saturated or non-saturated, saturated or unsaturated. Most these first acids, they naturally occur. First acid, this is something which naturally occur and have unbranched chain of even the number of carbon atoms ranges from 4 to 28, sorry. Then fatty acid, these are something which are usually found in organism. From where I've reached, is it clear?
Can you just repeat from the naturally occurring and have unbranched what?
Okay. It has got unbranched chain of either the number of carbon atom, which ranges from 4 to 28. And fast acid are usually, sorry, I didn't mention this. Fast acid are usually not found in organism. In their standalone form, I'll talk about standalone form as I go down, but instead exist as three main classes, which I will say ester, triglyceride, and phospholipid. And yeah, I've talked about three. Fast acids are usually not found in organism in their standalone form, but instead exist as three main classes of ester, triglyceride, and phospholipids. These are just my properties you need to know. Yeah, then first acid, the acid carboxyl we're talking about, this is the group function. I think by now I can't be talking about the group function. You know, we have been doing organic chemistry the other side. Then the radical R of the chain aliphatic. I talked about an aliphatic, the type of hydrocarbon of a long chain, which varies to give a characteristic of hydrophobic. Hydrophobic, I'm talking about the acid gras or the oil. I repeat one, what acid? Or the acid gras in short.
Yes, please, you can repeat.
Okay, I'll repeat again. A fat acid is a carboxylic acid with a long aliphatic chain. This is a long aliphatic chain. You're able to see? Let me check for another one. This is a long. Okay. I'm using your book, medicine. This is a medicine book. I decided to use this book today. I didn't want to make my own notes. Come back, you don't give examples. So I decided to use the exact book I normally use for medicine. Yeah. So right the end. I was saying a fat acid is a carboxylic acid with a long aliphatic chain, which is either saturated or non-saturated. Mostly the naturally occur fat acid have unbranched chain. Naturally occurring fat acid have got unbranched chain. What do I mean unbranched chain? This is what? It's a branch. This is what? There's a branch here. When I talk, they've got unbranched chain. This is the branch here. It's caving somewhere at a certain point. Now, the naturally occurring fat acid, it has got unbranched chain, which means it doesn't have something to branch. It's just a linear. It's in a linear form. That's what it means, unbranched chain. Then it has got it has got unbranched chain of either the number of carbon atom ranges from 4 to 28. That is a naturally occurring fat acid. Its carbon atom ranges from 4 to 28. But don't master about the number of what. Just know it. I'm just trying to let you know about naturally occurring fat acid. Yeah. And fat acids usually are not found in organism in their syndrome form, but instead exist as three main classes. They exist as three main classes, which I said of ester, triglyceride, and phospholipid.
Question.
Yeah.
When you're saying they do not exist in organisms in their syndrome form, what do you mean? What does syndrome? I don't know, syndrome. What does it mean?
Okay. When I say they don't exist, they normally don't exist in. Oh, sorry. I said they exist in ester, triglyceride, and phospholipid. They exist. Sorry, I said they do not. So, what I mean by saying they exist in these three forms, you find that in ester, triglyceride, of which I mentioned of the glyceride in the first place, where I said lipids are classified into two: simple and complex. In simple, we've got what we call glyceride. So fat acid, they also exist in what? In glyceride, which is a simple lipid. Am I clear? Or have I answered it clearly? Triglyceride is simply a simple lipid, which we're normally going to look at it specifically. I said we're going to look at glyceride, seride, and steroid. We're going to look at these three types, particularly in the next chapter 2, as we'll be finishing my lipids. Am I clear?
Yes.
Yeah. Then for acid gras or fat acid, it is classified into two. There is what we call acid gras saturé and acid gras insaturé. before I go there, before I explain about acid gras, what is acid gras saturate and what is acid gras insaturate, let's look at nomenclature of these acid gras. Before I proceed, I want to ask a question. Did you do Austin in organic chemistry?
Yes, we did.
You did, n'est-ce pas?
See,
So when I talk about trans and cis, you know these things, yeah?
no, we didn't start on that.
You didn't start from that.
Yes.
Okay. Don't worry. Don't worry. We'll try to look at it. So you don't know the configuration of E and Z. That's what you're trying to tell me.
Yes.
Then I have to start with the configuration, because here it consists of the configuration of trans and what? See, so I have to start with this configuration E and Z. Okay, I thought you did, you guys. So what can I do? What can I do? What can I do? Okay, we're going to try the way, we're going to see the way we're going to do it. Then I'll need to explain this pattern. Palas, I'll explain this at the end. Is it fine? I have to start with configuration. You didn't do. It's fine.
Yes, it's fine.
Okay. So yeah, but we can do a little bit of nomenclature. There are certain rules here you need to follow. Okay, let's do nomenclature. I'll just do it. Nomenclature. Okay. Let's say we want to name this acid, maybe acid palmitic, for instance. Want to name acid palmitic, which consists of 16, yeah, it's palmitic in fact, which consists of 16 carbon atom. What do we do? You know how you name, how you do nomenclature in organic chemistry, isn't it? Those rules, you look at the what's that rule before I state it?
You look at
The longest carbon chain, continuous carbon chain.
Yeah, you look at the longest carbon chain, which contains the multiple, yeah, something multiple constituencies. Yeah, you look at the longest carbon chain, which contains the multiple constituencies. That's what we look at. So from here, this is our chain, isn't it? This is acid palmitic, yeah, in French, acid palmitic. It contains 16 carbon atoms. I want you guys to know how we get this K7, of which you can start from here. Okay. Okay, let me start at anaerobic. I think that's when you know. For the acid gras saturate, the systematic, the way we write the formula, or the way we give it the formula or nomenclature, yeah, in short, the way we name the acid, this is the formula we have to look at. This N, it indicates the acid gras. So this acid gras we're talking about is the chain we're talking about is a chain branched or not. That's it. That's what this N looks at. Then when you talk about, when you see NC, we're talking about the number of carbons. Then this AN, it indicates, is the chain saturated? Is it saturated or non-saturated? We're looking at oic for saturated what? Acid gras saturate. Then I didn't mention this acid gras saturate. These are acid which this is an acid gras which does not contain a double liaison. Then the opposite is true for insaturate. Insaturate, it contains a double liaison. That's a key point you need to notice about acid gras saturate and non-saturate. Saturate, it doesn't contain a double liaison. Then insaturate, it contains a double liaison. Is it clear?
Yes, it is.
So, like I was saying, this is the formula used to name acid gras saturate, the one which is saturated. So this N, it indicates the acid gras. Is the acid gras normal? Is it branched or non-branched? Of which we have mentioned here that an acid gras saturate is an acid which does not contain what? A double liaison. Hence, it has to be normal. It's not supposed to be branched. Chain no branch. Then NC, this contains the number of carbon atom present in that acid. AN, this indicates the chain. This is something which indicates, which tell us the chain is saturated. Then we come here, the symbol, this CN, 0. 0 indicates the chain is saturated. This is what will tell us always. At the end of, I'll show you, at the end, remember about this 0, ask me about this 0. This is what will tell us, or whenever I'm in the question paper, I find they have named a certain acid gras and it contains 0. 0 has to tell you that this chain is saturated, or this acid gras is what? Saturated. Then when you look at CN indicates, N simply talk about the number of carbon present in the acid. From what I've said, is it clear?
Yes.
Then
Yes,
we're
it is.
going for insaturate. You see, this is for saturate. Have you seen the word? The formula, the way it's written? We come for insaturate. Now, for acid gras insaturate, as I earlier on stated that acid gras saturate, it does not contain a double liaison. Acid gras insaturate, it contains a double liaison. That's why you see this cough poor P. This is telling us this cough P, it's going to help us to know where the position of the double liaison is in the what? In the acid given. Or this is simply the configuration of P. The configuration P, it tells us the position of a double liaison, where the double liaison has been placed. Then NC, it tells us the number of carbon atom present in the what? In the acid. Then X, it tells us the number of double liaison. Is the number of double liaison 3, 4, 5? So it's just like the same way we are looking at in glucid. When it's 2, we say D. When it's 3, 3. When it's 4, tetra. When it's 5, penta. Just like that. Am I clear?
Can you just try to repeat on the number of carbon atoms in the X? From that, my network was trying to reconnect.
Okay. We're talking about how to name. We're talking about nomenclature. How to name acid gras insaturate. What I was saying is that this is the formula you need to know. This is the formula they use, or how they write acid gras insaturate. So this configuration P, conf P, this help us to know the position where the double liaison is. Then NC, it talks about the number of carbon atom present in the acid gras. Then X, it helps us to know the number of double liaison which are present in the acid gras given. Who was asking? Is it clear? X, it tells us the number of the double liaison present in the acid gras given, of which I said, if it is 3, you say 3. If it is 4, you say tetra. 5, penta. 6, and so on and so forth. Just like we did in, I think you also did this in chemie organic. Isn't it? Chemie organic, you also looked at this in glucid. Hello?
We're getting you.
Is it clear?
Yes.
Okay. Then the way you're supposed to indicate, or the outcome of naming of the acid gras insaturate, it has to be in this form: Cn, comma, or dot M, this triangle, M, the triangle, P, comma, P prime. Yeah, I'll explain what this P. Just try to look at this. This, I said, the way we name it is Cn, comma, 0. Always for saturate, they have to be 0 here. They have to be 0. It's the one which help us to say this is an acid graph which is saturate. Then for insaturate, it's a different, since it contains a double liaison. So it has to be different, of which in the first place, Cn is the same. N talks about the number of carbon atom present in the acid graph. Then M, and this triangle talks about the number of double liaison. Then P, comma, P prime. This talks about the position. Where exactly is it? So where exactly is it? That's when we give it the actual position where the double liaison is placed. So they say numérotation normal, Cyril la form. This, I said, remember, I'll come back up. I said, have you seen this form? Have you seen this?
Yes.
This is simply talking about the exact position where the double liaison is, or the double bond is. So let's go back here. I told you I'll come back to this. The way we count, or the way we look for the position where the double liaison is. Have you seen this? This is acid. Is it acid grass saturate or insaturate?
Insaturate.
Yeah, this is acid grass insaturate because it contains a double liaison, and you can see this triangle. Yeah, so to say. So the way you come up with a position, you start from the last carbon. Yeah, you start from the last carbon, counting, going to the first carbon. Am I clear? You start from the last carbon, going to the first carbon, for you to identify the actual position of the double liaison. So let's start. This is 1, 2, 3, 4, 5, 6, 7, and hence this is 7. And the symbol of P, comma, P prime is simply denoted this to tell you the position of the double, where the double liaison is in the acid graph insaturate. Is it clear?
Yes, yes.
Can you just repeat that?
Okay. The way we know the position of the double liaison in the acid graph insaturate, we start counting from the last carbon going to the first. Am I clear on that point? We start from the last carbon going to the first for us to identify the position of the double liaison. Hence, I started 1, this is 1, 2, 3, 4, 5, 6, 7. On 7 here, you find a double liaison. You find a double liaison.
What do you mean? Like we start from the last carbon? Because if what you're saying is true. Shouldn't the number like be like the bigger number until you reach the double bond? Like if you start from this other one, which is supposed to be ending like to 8 or something like that. It's confusing me. I don't know. I think you should try to elaborate more.
Okay. What I mean, you start from the last carbon, is it? The last carbon becomes the first carbon. First, in the first place, I asked you, do you know how you name, do you know how you do nomenclature for any organic compounds?
Yes, we do.
And what rule do you apply when naming nomenclature? You said you look at the lowest carbon chain, which carries maximum constituents. Hence, when I tell you name this compound, can you name it? Guys, naming this compound, can you name it? You normally start from here, isn't it? You start from here. It will be your first. Because looking at the number of constituents here, you can't start from here. You start from here. Because of this hydroxyl, you start from here. Looking at the principle used to name nomenclature. Now I said, following that principle of naming nomenclature, but just following that, let it be in order. Like you identify, this is 1, 2, 3, 4, 5, 6. You identify your longest chain. When you identify your longest chain, you take the last carbon atom present in that chain to be the first. Then you count the number until you reach at the double result, where the double result is found. Let's say if the double result were 2, let's take for instance, if the double result, in this case, there were 2. So we're going to count here. For the first one, 1, 2, 3, 4, 5, 6, 7. It's here, 7. Then let's take for instance, it's here. The other one is here. So we have to continue 7, 8, 9, 10, 11, which means here it's 11. So you say, so I told you it's P, comma, P prime, comma, prim prim, comma, prim prim prim. It continues telling you the number of what? The double result are there, which are there. Since here we're trying to identify the actual position where the double result is placed in the acid gram. I repeat, you start from the last carbon atom going to the first for you to identify the actual position where the double result is. Is it clear? Oh,
Yes, it's clear. Thank you.
okay. I'll explain about, this is just talking about the configuration E and Z. I'll explain about this, I'll help you. So, you know where the P and P prime is coming from?
Yes.
Where is it coming from? P and P prime?
It's signifying the position where the double bond is.
Okay, yeah, it's simply signifying the position where the double bond is, as you said. Thank you. Then I talked about the what? Acid gras, which are saturated. Isn't it? I said acid gras saturated, they don't contain a double bond. And they normally, normally acid gras, which is saturated, the number of carbon atom pairs from 4 to 30. They normally range from 4 carbon atom to 30 carbon atom. And the most common one of which you have to know it. It starts from carbon 14, but carbon 14 they don't normally ask it. But carbon 16, that is palmitic acid. You have to know this one, palmitic acid. Then carbon 14, that is let me remember the name. That is myristic acid. It contains 14 carbon atoms. Or let me write the word. Okay, I'll check it. I'll check it up. I think it's there, but down. Yeah, myristic acid. Then carbon, is it carbon 18? The one they like as well. I'm telling you, I'm mentioning the ones they normally ask mostly. It's carbon 16, carbon 18. Carbon 16, which contains 16 carbon atom, that is palmitic acid. Then carbon 18, stearic acid. This you have to know. Then there's carbon 20. Carbon 20, they call it arachidic acid. Yeah, I'm trying to use my memory. Yeah, arachidic acid. These are some of the examples of acid. Then on this saturated gras, we have got 3 types. Sometimes their chain are short, they've got long chain, and moyenne, they vary. I think here are the names. So mostly I talked about 4. You know what 4 is, how to butano, how to name your acid, hexano, 8, octa, 10, deca, you know all these things, isn't it? Then me, I'm interested in these. They normally ask this one, palmitic, stearic, arachidic. These are tatu. You have to know them. Then these, the same thing, palmitic and stearic, we normally find them in cooking oil, animals, vegetables, and the likes. That's why we normally find this acid gras. These, grains, we can say mass media, but in maize, I don't know what media is made of, but in maize, you find this thing. So guys, me, I'll emphasize on these 4, 1, 2, myristic acid, palmitic, stearic, and arachidic acid. These were being asked a lot. Is it clear? Hello, is it clear?
Can you please explain on the 4 types again?
What I mean, do you remember what this means? NC, what does it mean?
Is it number of carbons?
Number of carbon atom. Now I was saying the one which contains 14 carbon atom, which is tetra decanoic, yeah, is myristic acid. This is the normally asked in examination questions. They normally bring these acids. That's what I was simply trying to mean. So you guys, you have to know them. The one which contains 14 myristic acid, palmitic and stearic, arachidic, 20, 18, 16, 14. You have to know them. And these, you can normally find them in cooking oil, grains, maize, I don't know what meat is made of, animals in meat, and vegetables. That's where you can find them. Then arachidic, we can find them in maize. I think also in smida, I don't know. Smida is made of what? What is smida made of?
Kaya.
I think flour and yellow maize.
Yeah. No. I think it's wheat. Yeah, it should be wheat. Yeah, so you can also find arachidic acid gras, which is saturate. It does not contain any double bond. These do not contain any double bond. Is it clear?
Yes,
yeah, long chain, they contain 22 what until that number. Yeah, and the names are here. Yeah. Then we go for acid gras insaturate. Then acid gras insaturate, I said these, they contain what? Double liaison. And most of these acid gras insaturate, they have got a long chain of about 16 to 20 carbons. Like we had looked in the rules above. The only double liaison which is supposed to be established in the range of starting from 9th carbon to 10th carbon, somewhere there. 7, 9th, 10th carbon. That's why the first double bond is supposed to appear between the range of 7, 8, 9, 10. That's why the first double bond is supposed to appear when it comes to acid gras insaturate. Is it clear? Then when you talk about this, at multiple nesopa conjugate may separate par un group methylene, sekile plus, for example. These we're talking about, remember the tree, we're talking about the positioning of what? Of the double liaison. They are separated, they can't be congested, or they can't be joined, linked. No. Is it clear? So you find that this is at position 9, the double liaison. There it comes at position 12, it comes at position 15. Hence it becomes a 3. Am I clear? Then Then this double result for acid gras saturate, they normally form a configuration which is sorry, yeah.
Please repeat what you're just from saying.
I was trying to stress this point, which we said. I was stressing these 2 points. These are the rules general. Like the only place, the only time, in terms of, we're talking acid gras saturate, the only time you can see a double result, it must be at the carbon starting from 7, 8, 9, 10. That's when you can see a double result appearing. And this double result, they cannot be linked. What do I mean saying they cannot be linked? I'm coming here. They cannot be linked together. They're supposed to be separated. Let's take, for instance, here this is the double result in a spa.
Yes, it is.
Yeah, you cannot find another double result here. Jamais. That's what that point is trying to say. They are separated. You can either find it here or find it here. And they normally, this double result start appearing at the carbon 7, 8, 9, 10. Somewhere, that's when you can find the first double result. Am I clear? That's the point I was trying to stress. Then for the configuration, I also said a mention of the configuration. They make E configuration most, not mostly. Let me say most of, okay, let me use most of acid gras saturate make an E configuration. What is an E configuration? I'll get back to you. I'll answer you that question later. Don't worry. That's why there's this trans and sick. I'll answer you guys. So an E configuration is this one, then this one, trans is this one. I'll come and explain on this. Don't worry. Then examples of acid gras saturate. The one which we were asked, were told to retain is oleic, which has got carbon 18. This and linoic, yeah, carbon 18. This they normally ask a lot. Now, if I'm to ask you guys, what does 9 and 12 mean, represent?
I think it means the position of the double bond.
Yeah.
Yeah, it represents the position of the double bond present in linoic acid. Oleic acid, it's at 9. Then what does this one represent? Or these two? What does it represent?
Double bonds
So the number of the double bond in a molecule. Then we're going to say it's what?
9.
Eh? I didn't get you.
If it's 2, you say di. If it's 3, you say tri. If it's 4, you say tetra.
Okay, yeah. Can't you following? Yeah, that's all about nomenclature of this acid gras, saturate and unsaturated. Now, let me talk a little bit about the configuration. I will now go into chemistry. The configuration of E and Z configuration, isn't it?
Yes.
I want to teach you like a simple thing you need to, for you to determine first the E and Z. You look at the valence number. Let me say, you look at the valence number. Since you have been, maybe let's say for instance, you have been given different atoms here. You have been given different atoms. Now we want to configure this. Yes, I want to see. Do I have my book here? Okay, yeah. You want to configure this E and Z configuration. I thought Darius told me I shouldn't talk about this, but I'll just tell you. Yeah, in advance, you're going to learn. Yeah. So you look at the number of atoms, you check the number of atoms. All atoms, you look at it. Then you look at the valence number, or which one is more oxidized. You check amongst all the 4 atoms. You find that this one and this one who have the same, they are the same, n'est-ce pas?
Yes.
This one and this one have a different one. But what matters, what determines most is this one and this one. You look at these 2 first. That's what determine mostly. You look at these 2. That's another way of determining it. Look at these 2. These 2 have got the same. You start from this. This is 1, 2, 3, 4. You look at this one and this one. If they're the same, you say this is an E configuration, which is a cis. Then look, come here, come this side. This one and this one are different, n'est-ce pas?
We see.
Yeah, they're different. We talk about a Z, which is a trans Z configuration. Yeah, wait, let me confirm with my book. I think sorry. This is Z when these are the same. When these are the same, this is Z. Then when they're different, this is E configuration, a trans. That's a nomenclature of alcenes. I thought you did the E and the Z configuration. That's the simplest procedure.
Can you just repeat? My network is so bad.
Okay. You look at these 2. You look at these 2. You compare these 2. When you compare these 2, in terms of oxidization, which one is more oxidized? Or you look at their valence number. Or the other people use another formula, but I don't want to mention that formula. I don't want to complicate your mind, but I just want you to take a simple route. You just compare these 2. Is their valence number the same? Yes. If it's the same, it's what? A Z configuration, which is this configuration cis. Then if their valence number are not the same, they differ. You just look at these 2. Since we said when when I want to number these things, I said this is the first one, second, third, fourth. Yes, you look at these 2 mostly. Look at their valence number. Is it the same? No. If it's not the same, it's a E configuration, which is a trans. Am I clear? Is it clear?
I
No.
have a question. I have a question. Yeah, so how about when we haven't been shown like in this diagram form, for example, we've been shown in topologic form. How
Logic
do we
form of this, a trans and a A.
the to yeah, topographic form.
This in a topography form.
Yeah, how do we know like since here it's more like in this form, but when it's in that other form, how do you guess if it's a cis or a trans?
Aha. Okay. Can you let me see if I can open my organic what? Organic. Sign up Biochimie organic. Guys, this is what ecobiology. Just wait. Desktop. Chemie organic. Chemie organic perfect. Where is my folder? Folder for chemie organic. Oh, chemie organic. Just wait. Organic size. Name of compound. Chemistry. Just wait, I'm looking for principle from English. Am I going to find it? Just wait a minute. It's trying to open. You're able to see? You guys, are you able to see?
Yes, we're able to see.
Yes, yes.
Okay. Let's look at this. Since you said that there is H and R and what, let's look at this. These two. You see this? This is what? What compound is this?
Yes,
Then the way we do the numeration is numeration. The numbering is 1, 2, 3, 4. Hence, one, we look at the first and the third. Then you look at their valence of these two. We look at their valence. Are they the same? Are they the same?
Yes, they're the same.
They are the same in a spa. What do you say? You put Z. Is it Z or A? Let me ask.
Z. Z.
Z. That's a Z configuration. You come here. This and this, are they the same? No. You put E configuration. Is it clear?
I think you've explained something else. The person who was asking about the compound being represented in a topologic form. How can you tell that this is a Z arrangement or E?
Topological.
Yeah.
Just wait. I want to look for a topological diagram. Formation, steroism, dimension. Okay. Wait. Let me look for the TD we had used. When I find the TD, my TD, then I'll show you guys in a topological manner. Kondwan.
Yes, please.
You're the one who was asking?
Yes, it was me.
Okay, yeah. I'll get back to you if I find my TD. Yeah, but though in biochemistry we don't do that. It's for chemie organic, but I'll answer you for the sake of answering you.
Okay.
Yeah. Is it clear from the from what we have looked at? We have talked about the introduction, what these lipids are, where do they originate, classification, biological rule. We have looked at acid gravish fat acid. We have looked at the two types of fat acid, saturated and non-saturated. Is it clear so far from where we have reached? Eh? You guys, is it clear?
Yes, it's clear. Just kindly repeat on the P primes. I was a little bit behind.
P primes. When you talk about P primes, this is the first pair. Let me come here. It's a good point. It's a good question you have asked. I'll say this is P. This is P prime. This is P prime prime. What do I mean? These are the position of the double réseaux which are present in linoleic acid. There are three, which are three, and they're pressed on 9, 12, 15. This is what we call prim, the first P prim and P prim prim. So when I come here, I can say this is P prim, P prim prim, P prim prim prim, P prim 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 prim. 5. Is it clear on my P prim prim? It's just that depends on the number of double bond present. Like here, the double bond is situated on the carbon atom, which is number 9. Here on number 12. So this P prime, there are 2. Is it clear?
Yes, it's clear.
Yeah, can I have a good question?
Yeah, I have a question. Can you just explain on this series column?
On the what?
This column, that I just says W7, W6.
This, this column, what does it mean? I told you. This, what does it mean? The first where the double réseau appears.
Yeah, it shows where the first double liaison appears, right?
Yeah.
And then we had made mention that usually the double azoles start from carbon 7 to 10
6,
somewhere
7,
there.
what? Yeah, yeah.
But then down here, there's this one which says 3, so it just confused me.
Ah, yeah, according to science, according to scientists, that's what they found: linolenic acid gras. That's what they found, and they normally found it present in what? Grains. Yeah, but mostly, I said mostly carbon or acid gras insaturated. They are found in the range of 7, 6 to 10. That's where the first what? The first bond appears. Mostly. Yeah. Questions? Hmm? Questions? I start asking questions.
I think you can just repeat on the same series.
On
The series.
this.
Yeah.
Okay. Coming to our nomenclature. This, the same cup, this is a series. This is where this is used to denote the position of the first double azole. Present in acid gras insaturated. This we use it to denote the position of the first double azole present in the acid gras saturated. And I said that we normally start counting from the last carbon atom going to the first. We start counting from 16, the last carbon atom. 1, 2, 3, 4, 5, 6, 7. And we note 7. The first carbon, the first double azole is at 7th carbon atom. Am I clear? Is it clear?
Yeah, it's clear. I've seen now.
Questions? There are no questions. Kondwan.
With DM, talked about properties of sugar.
Kondwan, I can't get you. Anyone who is getting Kondwani?
No.
Okay. Hello?
Yeah, I'm getting you.
Sorry, boys. Can you get me now?
What are you saying?
Yeah. So last time we talked about one property of sugars, and we said it's soluble in both water and non-polar solvents. Now, they will define lipids as those that are able to dissolve in other words, in organic solvents such as methane, but not in water. So can we say sugar is a type of lipid?
can't get you.
So
You said
so
the way we defined lipids, we said these are heterogeneous organic compounds which are insoluble in water but soluble in organic solvent. Yeah, now
yes, exactly. Then we also talked about sugars. We said they are soluble in water and also in nonpolar solvent.
is there anyone getting what Kondwan is trying to say?
No.
Kondwan, you can kindly inbox me with your question. It's like I can't get you from here. Your network is not stable. Then when you tell me the question you're asking, I'll come and explain it to the people, or I'll tell the people the question you were asking. I think that way will help out. Is it okay? This chat box. Yeah, that way it will help out. Yeah, are there any other questions? Are there any other questions from what we have looked at so far?
I can ask. I have this
Yeah.
question. I don't know if it will make sense, but you're talking about insaturated having double bond. So is there a possibility where you can have a triple bond, and how would you call that fatty acid if it's there?
A triple bond? No. A triple bond as in how? Like we've got a double result here, another double result there, another double result there.
No, as in carbon to carbon, and it's a triple bond.
No.
I'm asking if it's there.
Mutale, you cannot have a triple result or on this what? Zigzag. Do you remember the rule you learned in organic chemistry? Who remembers? I think you talked about this with Daliso.
Yes, we did.
Yeah, you can never have a triple result in a zigzag. C'est impossible.
No, I don't mean on the plain zigzag. As in, is there like a fatty acid that has like triple bond?
No.
That was my question.
No. Are there any other questions?
Even as you wait for other questions, can you just scroll down to that table? I want to look at something.
This table. Yeah, I was just trying to tell you the acids.
The one for the insaturated one.
Insaturated.
Yeah.
Oh, I didn't mention of this. And this acid graph, they normally ask it. This one, arachidonic. Yeah, I don't know the pronunciation. The pronunciation is those guys. This one, oleic acid. They ask it a lot. I think you have these books, guys. I send you this book. Have you seen? Are you having this book? Or maybe it's not too.
I think you should just resend it again.
Okay, let me tell you where it is now. Okay, it's like so much again. The link I sent, where I told you, it contains books. Okay, I'll show you. I'll circle it. Maybe never. Okay. I'll start asking questions. Random. I'll be choosing random. Esther. Esther, is Esther there?
Yes.
Yeah. What are lipids? And tell me 3 laws of lipids.
Okay. Lipids are biomolecules that are insoluble in water but soluble in organic non-polar solvents. And the 3 rows of lipids are biological. Should I explain them or I just name them?
Explain to us, we don't know.
Okay, biological, which
The
the
biological laws of lipids.
yes, the biological roles of lipids, they deal with the energy reserves, how energy is stored in the body. Yes. And then structural lipids, structural roles, sorry, deal with protection, like the membranes, the cell membranes. Yes. And then metabolic, you said that we'll look at it later. Yes.
Metabolic, we talk about the synthesis of hormones, so to say, in the body.
Okay.
The other one.
Awesome.
Yes?
Oh, okay, let just finish taking it then. I'll when she finishes.
I'm done.
You have forgotten one row. Structure, energetic, or metabolic. Okay, thank you. Yeah, wanted to come in.
Yes. You can go down to the table SP2 for the unsaturated things. I just made the conclusion of my hypothesis.
Insaturate, saturate.
Unsaturated.
Saturate.
Unsaturated. Okay. Yes.
Yeah. You have this book, guys.
So,
yeah. Question?
So like I was just wondering, like if you see, so this part I was looking at, I just got a random one, is carbon 20. The one which was carbon 20. Then for the series it was W6. Yeah, this same one is on top in the carbon 20 row section.
W6.
Yeah. Yes. So I noticed something. When counting the number of, like the position of the double bond, we start from the last carbon and count it as number 1. So I just made a rough topologic thingy, and I realized that for the W6, for getting the position, they more like they counted like from the normal, like from the first carbon up to like the point where it was saying the 6th carbon. That's where, like, how can I put it? Okay, let me restart. When counting the double bond, we start from the last carbon, and we find that the first double bond was on the 5th carbon, right? And then we continued all the way. There were 4 carbons. Now, if you look at this 4th double bond, the last one, you find that it is the 6th one if you count from the first carbon bond, which seems to be this W6, if I can put it that way. So now, the conclusion is it that, yeah, calculating and counting what the double bonds and all, we start from the last one, but with respect to the series, it's from the first carbon.
Calculating?
Like this series, the W3, W6, W what? These are not counted from the last carbon, but from the first carbon, right?
on that one, I can't assure you from the first and the last, because there is another way of calculating, coming up with the W series. There's another way of calculations. I don't really know it, so to say. That's why I didn't want to teach you. I wanted to teach you the other one. Yeah.
All right, can I? More like
Kenneth, but I'll get back to you. I'll try to calculate for each and every what. I'll try to calculate and I'll get back to you.
Yeah, I'm also just trying out another one to see, but okay, right. Thanks.
Okay. Blessing.
Oh, yeah, I just wanted to like see if what I've observed is the way things are, like in line with the question Kennedy had asked. Like when we get this acid which has 20 carbons. Yeah, when in terms of numbering the carbons, we are starting numbering them from the carbon which has a functional group, right? That's the first carbon. Or how are we doing the numbering? Are we starting from the carbon which has the functional group, or we are starting from the carbon which is just, yeah, which is not having a functional group? Yeah.
Guys, remember, to each and every rule there are exceptions. I can see you're getting confused of 3 and 6 here. Then it has got 11, 14, they've got all these things. But to each and every rule there are exception. So Kennedy, I'll try to calculate what you have said, then I'll respond to you. Yeah, but for calculation, they taught us, but I didn't get it as well. But I'll try.
All right, thanks. I'll do it.
Yeah. Any other questions? Okay. I'll take it as.
What does that small w again mean?
Who can help us? Guys, who can help us?
That's the position of the double bond.
Yeah, that's the position of the double bond. Then Kennedy, we are going to do a research together. Yeah, for the what? For the 6 and 3 position. For the one for the 20 carbon atom present. Then I'll get a random person here. Blessing. Name 2 types of acid graph and explain them. How do they differ? Explain how they differ.
We have the saturated ones and the unsaturated ones. The difference is that the saturated ones don't contain double bonds, while the unsaturated ones contain double bonds.
Okay. Can see my get. Yeah. So guys, now we're going to go for the TD glucids. There are certain people who inboxed me with their responses, and they needed explanation. They wanted to know it bit, and I'd explained to them, and we agreed that if I explain to you, which means you're going to help me explain in class, then why they are not clear, why your friends are not clear, I'll explain. So I invested my time in them. Now they have to invest their time as well in you guys. Then I'll be here. If it's not clear, I'll be re-explaining. I think there are 3 people who inboxed me with their responses. Taonga, who is this one? Taonga Taonga, your friends, Lydian and Blessing. Yeah, I think your flow is yours. You can explain to your friends. You guys have got the TD, Lucids. Do you guys have the TD with you?
Yes, we do.
Okay. I let you share the screen.
No.
Now I'm going to be explaining.
Okay, share the screen. Then we'll try to explain. Do the sharing.
To try, yeah, you have to. I invested my time in you guys. You have to. Me, I'll help you out where you fail to explain. Let me look at the question. Okay, I'll just go direct to I'll share the response. Then they'll be reading out, you'll be reading out loudly the question, then we explain what it means. It's fine that way?
Yes, I think so.
Then at the end, they are going to share with you the responses. I think I gave them the responses, I answered them. Just wait. You know, all I wanted, I just wanted to see a rough sketch of anything you understood from there. I didn't mean like I want final answers. No, I just wanted a rough sketch, anything. I think Kennedy inboxed me, but you inboxed me today. Isn't it? Kennedy.
Yeah,
when did you inbox?
Somewhere 23.
Yeah, that's what. Yeah. By that time I was occupied. Just wait. Down, and I'm not doing my questions. My answers. Down. All right. Yeah. Just wait a minute. I'm looking for responses. Taonga, you're going to explain question what? I guess we did 2, 3, and 4.
We can all explain a question, like just take up certain things. Are we supposed to get questions individually?
You explain, then if you fail to explain, your friend comes in. I guess that will be helpful. Then I'm there. Now I want to see what you understood.
Okay, I'll explain question 2.
Okay. Then you guys don't worry, I'll send these responses in the group, eh?
Thank you.
Yeah, I'll send you guys. Like I was saying, you guys, mind out, we're learning difficult steps here. But when you go there, it will be a walkover for you guys. You're able to see? Able to see?
Yes, yes.
Sorry?
Yes, you can see.
Okay. So I think you can start explaining. It's the second question. Somebody read the question, or you, I don't know how you're going to do it. Just be telling me move.
Okay, may we have someone to read the first question from exercise 2?
Guys, there's one person who has left. Or we are 10, just like this. Anyone to read? Kenneth?
Okay, yeah, so exercise 2, underglycid. Le tétraholocide Q est composé de mannose, galactose, glucose et fructose. A. Avec le liquide de félin, il donne...
Féline? Avec des liquide de
féline.
féline? Oui.
Voilà. Il donne un précipité rouge brique. De
Okay.
Q.
Okay. Wasila, explain that from that statement.
Okay.
What do you understand?
So from my understanding, we were given...
No. Pose the question to your fellow what? How are you going to let them understand what?
Oh, okay, you guys, what do you understand from the first statement?
They're quiet, which means they don't understand anything. So explain now.
Okay, so from my understanding, we have a tetraholoside Q. This is a glucid, which is made up of 4 sugars. And here they have named the mannose, galactose, glucose, and fructose. So now our obligation here, we're obligated to find which sugar is which one takes up the position A, or which one takes up the position B, C, D, which one is making sense, which sugar has got which position in this compound. Are there any questions? Seeing as there are no questions, so from here I separated the tetraholoside into 4 without naming the, I just used some letters to denote them. I used A, B, C, and D, as you can see on the answer sheet there. So the A, B, C, and D don't really insinuate that maybe mannose is A, maybe galactose is B. No, we don't know which one is which yet. So we have to now look at the questions which were given to us. So the first part, as Kennedy read, avec la liqueur de féline, il donne un précipité rouge brique. So from what Deniso taught us last week, we know that one of the properties, the physiological properties of sugar are that they undergo oxidation. So when they undergo oxidation, some sugars, this is like oxidation with a transition metal. So some sugars will give us a red brick precipitate, but what type of sugars will give us that? That's a question I'm posing to you guys. Yes, so that's a question to you guys.
For the sake of time, just continue.
Okay, so from our lessons, if you go back, you realize that This liquor de Fehling is used for to identify aldose sugars, the ones that have got a free carbon. The first sugar is free. Yes.
Okay.
Yes. So the first and aldose, the first for this for this reaction to be positive, the first carbon has to be free. Yes, the first carbon has to be free. So here in the statement, since they have told us
At what? For reaction to occur, the end terminal of a given chain, it has to satisfy two conditions. The first condition, the first carbon is for a relieved. The second condition, it has to be an aldose for a reaction to occur. Continue. I'll just clarify.
yes, exactly what Laston has said. So in this case, when we look at the answer sheet, we have A, B, C, and D. So here we're going to test the end sugar, which is the D. So if D is supposed to qualify for A, it has to be have the qualifications of it having a free libre, a free carbon, and also it should be an aldose.
The
So
first carbon, emphasize the first carbon has to be free.
Yes, the first
and it has to
carbon,
be an aldose.
yes, the first carbon has to be free and it has to be an aldose. So in this case, our D has already gotten the position of, okay, we're saying our D is glucose in this scenario because this reaction was positive. As you can see that we're given a brick red precipitate. Are there any questions? Okay, we're moving on to B. Can anyone read B for me?
Okay, if I continue the reading. D. Q in more de Q in alpha glucosidase libère une mot de glucose et une mot de triholocide T. Yeah.
Thank you, Kennedy. So for B, we're saying on 1 mole of Q, a alpha glucosidase liberated a mole of glucose and a mole of triholosides. So in this scenario, alpha glucosidase is an enzyme. It's an enzyme that liberates glucose and any other sugar. In this scenario, we're given glucose and a mole of a triholoside. So here we know that our D is our first sugar that we found is glucose. So we know that glucose was found. So we found wait, I'm confusing myself a bit. So we know that we found glucose. Yes. So the other triholoside can have either mannose, galactose, and fructose. Yes. So here on the answer sheet, you're going to see the formula that came up. We denoted the first sugar we found as A, which is glucose, plus T, in brackets B, C, and D, which is a triholoside. We said since we know one sugar, only 3 unknown sugars can be in the triholoside. And then the alpha glucosidase is an enzyme that will always give you the sugar that will give you always be the first one because it's alpha. Yes. Does anyone have a question there?
Yeah, actually I have a question.
Yeah, sure.
On the first conclusion that you made, I don't know how you arrived in a conclusion that is glucose, in that from this reaction, it's liquid the selling thing. It is either the first carbon is libre or bien, it is an aldehyde. Now, from this list, we've got mannose, galactose, fructose, glucose, of which fructose is a cetose, and the rest have got the aldehyde functional group. Now, how did you conclude with the first statement that it is glucose? Why not galactose, bien, mannose, and yeah.
Okay. From there, I think it's my mistake. I concluded before I was supposed to conclude that it's actually glucose. So if we combine A and B, that's when we can actually justify that the first sugar.
Sorry guys for what? For this interruption. Yeah, I'm going somewhere, but Daliso will be here. I've left Daliso will be explaining where you don't really get the thing. Yeah, it's only the TD. That's where you help out. Yeah, I was sorry for that. That's a video for a music. Yeah, I was trying to show him what to turn when to find the what is going to find the responses for the TD. Yeah, you can continue.
So Kennedy, as I was saying, for this one, I concluded fast because I don't know I concluded fast, but then you are right. That's a correct analysis. So if you put A and B, if you combine the statements A and B, you can actually see that the first sugar in the tetraholoside is glucose, because as I said before, an alpha glucosidase is an enzyme that will give you glucose as the first sugar, as the alpha sugar. So in this case, we can safely conclude that A is glucose because it has because it was liberated by the alpha glucosidase. I don't know if I'm making some sense there. Yeah.
So what you're trying to say is that first you have to solve B, then now you can conclude that it's actually glucose and not maltose or galactose. That's what you're saying.
No, just a minute. Can everyone get me first?
Yes, we can.
Now, I don't have the question paper. Okay, the question paper has been brought to me. Now, let me just read the question. Then I'll help Taong explain. A very good explanation, Taong. So it says, la trioloside Q est composée de mannose, galactose, glucose et fructose. Then the first reaction is avec la liqueur de fémine, it donne une précipité brique rouge. Then the second one is sur une mole de Q, une alpha glucosidase libère une mole de glucose et une mole de trioloside. We end here for now. So the first reaction, like you guys were taught in the other co, we are saying, first of all, we are supposed to have a carbonyl function that is libre, and one aldehyde is supposed to be libre. It's supposed to be at the far end, either in the beginning or at the far end, and it's supposed to be libre. Now, in this case, we are saying, avec la réaction ou bien avec la liquide de fémine, il donne une précipité de brique rouge, c'est-à-dire la réaction est positive. Now, here we have how many aldehydes? We have mannose, we have galactose, we have glucose. Now, Taonga comes in with the response of glucose because the enzyme glucosidase gives the direction of which glucose is starting. So in other words, what Taonga was supposed to say is the enzyme alpha glucosidase is what gives the first glucose the first saccharide molecule. that is going to start in the chain. So just like, I don't know if you guys have the TD, all of it, there's an exercise on, you have the TD, do you have the TD, all of it, like from question 1 to question 4?
Yes, we do.
Yeah, we do.
When you go to exercise 3, it says, un dioloside est oxydé par le bromine au milieu alcaline. Après hydrolysis et chromatographe, on identifie l'acide gluconique et une dihydrohexose. Le dioloside est soumis à perméthylisation complète suivie d'une hydrolysis. On obtient une ose, quelque chose que... Then, le dioloside de départ est hydrolysé par beta-galactosidase. So it means it's automatic that the first molecule that you're going to have is going to be a galactose, because it is the enzyme that directs. In other words, what it is that you have a chain of molecules. You've got A, B, C, D. The enzyme always reacts with the first molecule. It will react with A, then go to B, then go to C, then go to D. That's the way it's supposed to flow. So the first reaction avec liquid de Fermi just shows us that, okay, at the first, maybe A, like the chain here, like the chain you can see, this chain you can see, just a minute. Maybe this chain you can see here, you say A, B, C. Maybe the A here is going to be, what's this? An aldose. Maybe this D also is going to be an aldose. Why? Because in the case where the reaction avec copper 2, the complex cation, you are supposed to have a formation of a red precipitate. So there are two cases, like we stated last time. We are supposed to have one that is a libre here, that is carbonyl, and it's supposed to be an aldehyde. Same applies to the last one here. So we do not know. So the first reaction just shows us that maybe the first letter here, the first glucose or the glucid molecule will be an aldehyde. Same applies to the last one here. Maybe it might be an aldehyde. Now, B is what tells us which molecule is starting in the chain. So it has stated to say that this tetraholoside reacted with an enzyme, or there was an enzyme reaction with this holoside. Now, when the reaction happened, the enzyme started with catalyzing this, then it went to this, then therefore acid the sweet. So the enzyme gives direction on which glucose or glucid molecule is going to start. In our case, the alpha glucosidase started with A, and that is the reason why we have a glucose molecule and we have a triholoside B, C, D. Is it clear? So
yeah, it's clear. And
yeah,
one question.
Yeah. Yes, it is. Okay. So Taonga can continue.
Before she continues, can I ask a question?
Yeah.
So we're saying this enzyme alpha glucosidase reacted with a glucose in China, but it was the first in the chain, right?
Yeah.
So what would have happened if, let's say, it was, let's say, second in the chain? Would it have reacted? What would have happened?
No, So in a case where you have the glucose molecule positioned at the second, in the chain here, in the second, what do you call it? In the second position. If you look at the molecules on question 3, when you go at the far end, there is what you call the perméthylisation reaction. Is 2, 3, 4, 6 tetra O methyl glucose 2. That's 2, 3, 4 tri O methyl galactose. All those things. Have you seen them in your TD? Have you seen them in your TD?
Yes,
Yeah, at the far end there. So what our professor told us was the key that you're supposed to use when you're answering these questions, where you're determining which sugar is starting and which sugar is ending. When you have a tetra, the tetra will always be at the beginning or at the end. A tetra will always be at the beginning or at the end. Now, in this case, we have a tetra. Then the tri will be at the tri. The ones we call tri will be a tri. They're always going to be in the middle. They are always going to be in the middle. I don't know how, I'm not using my PC. I would have showed you a PowerPoint presentation. I'll do this tomorrow. You remind me. I'll explain how you find that the tetra and how it's branched to those things. But the tetra, every time the perméthylisation reaction should be your guide. Every time you have a perméthylisation reaction, it should be your guide to say, if you have a tetra will always start. It will either be at the beginning or be at the end. Now, in our question, we have the tetra beginning, that is 2, 3, 4, 6 tetra or methyl glucose. Now, another question can be posed to say, okay, Dallas, you're saying the tetra is supposed to be in the first position or the last position. Now, to counteract that question, I said the alpha glucose enzyme is the enzyme that is going to catalyze the first molecule here. So it's automatic that the first molecule will be a glucose molecule, in that it's also justifying the permetylization reaction, which is 2, 3, 4, 6 tetra or methyl glucose. So when you have a glucose molecule positioned either at position B or C, you are supposed to have either a D or bien a tri when you look at your permetylization reaction at the far end. So please take note, the reaction, the permetylization will always be your guide. They will always be your guide to say, okay, this molecule is at the end, this molecule is at the beginning. Is it clear? So permetylization, reaction, attention. Is it clear? Is it clear?
Yeah, it's clear.
Yeah. So I don't know how far you guys are going to go with the TD, but when it comes to exercise 3 and 4, I'll come in and explain why the permetylization reaction plays an important role in discovering which one is going to be at the beginning, which one is going to be at the end. Yeah. Yes, let's hope it's clear for everyone. No questions? No questions? Tong, I can proceed.
Okay, so Delisa has explained A and B and why our first sugar is glucose. So we move on to C. So may I have someone read this for us? Okay, I'll read it. Te è soumis à une oxydation par l'âge et milieu alcaline suivi d'une hydrolyse donne un produit acide. So T underwent oxidation by iodine, and then and this oxidation took place in an alkaline solution, and then hydrolysis was so let me start again. T was oxidized by iodine in an alkaline solution. Next, hydrolysis happened. Then it gave an acidic product. Yes, an acid as a product. Yes, which means this oxidation was positive. If we remember what Daliso taught us about the properties of sugars, we have the sixth property, which is sugars undergo oxidation by halogens, and if it's positive, then if it's positive, then an acid will be given as a product. Yeah. So from here, from our question mark, our marking key, sorry, it gave an acidic product which is positive. So for us to have a positive reaction, it has to take up the conditions of it being an aldose, and it's also supposed to take up the condition that its first carbonyl group is free. Yes, for the reaction to be positive. So since we know what A is, and we know that the triholoside here, which is T, is comprised of B, C, and D, So here we thought that from the three, we're thinking that it can be either mannose or galactose because these are the only aldose we have. Yes. So for C we'll leave it like that until we see what D is talking about, then we can make our conclusion after that. Are there any questions? We can move on. Yeah.
Yes,
So
we can.
can someone please read D for us?
Okay, this says T est traité à la phénohydrazine à chaud, puis soumis à une hydrolyse. On identifie un glucosésone. Is it the one?
Yes, it's thank you, Kondani. And then from here, we say that T was treated with a phenylhydrazine, and we know that from our properties, they can be sugars can be treated with phenylhydrazine to give us a glucosazone. Yes. So from here, we go to our marking key. It says then T was treated with phenylhydrazine, yes, and the observation was that an osazone of glucose was given. So for an osazone of glucose to be given, we can have either mannose or fructose. We can't have galactose because, well, from the notes that Daliso gave us and the explanation, he said galactose can't undergo a reaction with phenylhydrazine because of its structure and its chelarity. Yes, if I'm not mistaken. So here the osazone was mannose and fructose are osazones of a glucid, and these are the ones that can undergo this. So from here, we further went on to look at, we now have to compare C and D. Yes. So
What's happening?
oh
Okay. I thought you have gone out.
no, I'm still here. So from here we said there's no way that D can be galactose. So we said that D is mannose because mannose is an aldose and it can undergo a reaction with phenylhydrazine, and it can also undergo a reaction on C, which is with oxidation with iodine. But then for that one, since we're dealing with the last sugar here in the chain, which is a D, I was thinking that we use D as D should be mannose. Yes. Then from there we have C as fructose because it's in between. Then we have, okay, before we actually say this, let's just read C, D, and E. Yeah, can someone read E for me?
So I'll read. Is it E?
Yes.
So si notre Q, si notre mot Q, l'action successive d'une alpha-glucosidase puis d'une bêta-galactosidase libère respectivement une mole de glucose et une mole de galactose. F, Q est soumis à une perméthylisation, suit d'hydrolyse acide, on obtient le dérivatif méthyle suivant. Des 2, 3, 4, 6 tétraométhylglucose, 2, 3, 4 tri-ométhylgalactose, 2, 3, 6 tri-ométhylmannose, 1, 3, 6 tri-ométhylfructose. Pour proposer une structure de tétrahydrolysate Q qui tient compte de l'ensemble des résultats précédents.
Okay, thank you, Daliso. And so, like from E, we are told that another mole of Q is undergoing a successive action of glucose, alpha glucosidase and beta galactosidase to give respectively glucose and galactose. So, glucosidase. So alpha glucosidase, as we saw in B, gives out a glucose, and we've already identified that our A sugar is glucose. So our B sugar will be galactose because beta galactosidase will give us galactose. So which means the remaining is our C and D. So here, when we look at what we're remaining with mannose and fructose. So now, according to what I remember last time said, he said that acetone cannot be at the end of a chain, like it cannot be at the end of a complex sugar chain, but an aldose can. So in this scenario, we're going to have mannose as our D, being the last sugar, and then our fructose is going to take position C. Yes, is that clear, or are there any questions?
No, just to clarify, if there are no questions, are there questions like Taonga is saying? Okay, so just to clarify, it's not that you cannot have acetone or cetose at the end. No, the reason why you are not having acetone in this case at the end is because the question says the first principle, which is the first reaction, which is avec la liquide de féminin, la réaction donne une précipité rouge brique, c'est-à-dire la réaction était positive. In the case where the reaction is negative, it would mean that at the end or at the beginning of this molecule, we have either the two conditions which are not satisfied. The first one, which is the carbon number 1 is not libre, and the carbon number and the two carbons at the end, or the two functions at the end, might be one, it's acetose at the beginning or at the end. It is not that you are not supposed to have acetone at the end. No, you can have acetone, you can have an aldose, all those things. You can have an acetone or an aldehyde at the end, at the beginning. But what we are looking at here are the conditions that these glucose molecules or the glucids were subjected to. So the tetrahydrolysate was subjected to a reaction with liquid féminin, and the reaction was positive. So because the reaction is positive, it disqualifies fructose to be at the end or at the beginning. Why? Because first of all, it's not an aldehyde. It does not have the carbon that is at number 1, and the carbon at number 1 isn't libre for fructose. That's the reason why fructose would not be at the end for this question. But it is not a convention that you're never going to have fructose or any cetone function at the end. No, we are always supposed to satisfy the rules that we've been given. The reactions that we've been given are going to govern us. Is it clear?
Yes.
GM, can you please repeat a little bit? My network was horrible.
So I am saying the generalization that was brought up to say you are always supposed to have an aldehyde or an aldose at the end or at the beginning of a reaction. At the end or at the beginning. Just a minute. Yeah. here. The generalization that was brought about to say at the beginning and at the end, you're always supposed to have an aldehyde on aldose is not true. Why? Because we are given reactions, like these molecules are subjected to reactions. Now, when you subject this molecule to a reaction, you expect either a positive or a negative reaction. Now, in a case where you have a negative reaction, it implies that it has not satisfied these conditions here, which is, c'est-à-dire, il s'agit de deux conditions. La première condition, it is supposed to be an aldehyde, and the second condition is the carbon at number 1, that is carbon number 1, is supposed to be lib for the reaction to be positive. Now, if we are saying that we are supposed to have an aldehyde here, it would mean that this reaction will be positive, and we are going to have a brick rouge precipitate. Now, what if we had fructose here? Now, if we have fructose here, this reaction would have been negative. This reaction would have been negative, and it does not satisfy these two conditions. So now what I'm trying to say is the generalization that says you're always supposed to have an aldehyde or an aldose at the beginning, at the end, sorry, and at the beginning of a glucid or a saccharide molecule is not correct, because we are subjecting these molecules to different reactions. What if it was subjected to what do you call this reaction? There's a reaction that we looked at, the one that Tawanga was saying, this one here, soumis une réaction avec iodine. When you have a reaction with iodine, it's supposed to be the same principle, which is the aldose and the carbon number 1, and you're supposed to have the giving of is it the production of an acid over the glucid, an acid over the glucid. Now, for you to have the acid of that glucid, you are supposed to satisfy these two conditions as well. So it's not conventional that these will always be no. When you're reacting a glucose with what is going to this glucid molecule with this is going to give this. No, the reactions that are what's going to tell you what is going to give what. So for this one, it has been found that at the end here, if we have a fructose molecule or a setose molecule, it will disqualify reaction number 1. So if it disqualifies reaction number 1, it totally also disqualify reaction C, because with further analysis, you find that the carbon 1 is actually not even does not even have the aldehyde function. It's the aldehyde function at position number 2, which has this is the setose function. At the end of the day, it will disqualify everything in this question. So it is not conventional. Please take note. It's not conventional that you're supposed to have a galactose, a mannose, or a glucose here. It can either be a galactose, a mannose, a fructose, anything here. But what is giving us direction is what reaction gave what, and was it positive, was it negative? Then we look back to our properties and say, okay, if it is a positive reaction, we are supposed to have this. If it's a negative reaction, we are supposed to have this. Then what conditions stand for a positive reaction, and what conditions stand for a negative reaction? Is it clear?
Yes, it is.
All right. You can carry on, Tawanga.
Moving on, we have identified that our first sugar is glucose, and our second sugar is galactose, and our third sugar is fructose, and our last sugar is mannose. Is that okay? So for F, it's yes as diglyceride. Q is subjected to a permethylation process, and next to an acid hydrolysis, yes, and we obtain the following methyls here. So we have 2,3,4,6 tetra or methyl glucose, 2,3,4 trimethyl galactose, 236 trimethyl mannose, and 136 trimethyl fructose. So according to this, we'll write them down as like the layout on the question on the marking key. Yes. So now here we're going to draw circles. Yes, we're going to draw circles in the order of which the sugars were found. So we're going to, when you look at the other, oh, Daliso, may you go to the other part of it? Yes, there. When you look at that page, we're going to we have glucose, galactose, fructose, and mannose. They're laid out there as circles. So you can be wondering what the numbers here around are in the shells there. I can call them the shells for now. So according to what we're given in F, the information we're given in F, we're going to place the numbers of each respective sugar in its shell. So like for glucose, we're going to start with 2, 3, 4, 6. Like we'll place them there. And when you're placing these numbers, always know that you're moving in the clockwise direction. You always place them with the first one moving in the clockwise direction. Then on top there you can see a 5. That 5 is the position of the oxidic linkage. Yes. Remember Daliso was teaching us last week about Haworth and
Tolling.
yes, Haworth and Tolan. So from there we learned that for an aldose, the oxidic bondage is between 1 and 5. 1 and 5, carbon number 1 and carbon number 5. That's why the oxidic linkage is found. So in this scenario, we're supposed to identify that in one of, like we have to acknowledge that in on the shell of each sugar. So the next shell we have there is galactose. And for galactose we have, according to our information here, we've got 2, 3, 4. But galactose is an aldose. So we're going to put the 5 there because that's why its oxidation linkage is on the first and the fifth carbon. Yes. Then we go to our fructose there and we replace likewise. Fructose here has come third because that's the order in which we found the sugars in this specific experiment or specific analogy we're given. We didn't use the order which they gave us in F, like glucose, galactose, mannose, fructose, because that they're just writing it. But for us, we analyzed everything and we are putting them in the order in which they were found. So our third sugar there is fructose with 1, 3, and 6. And fructose is a cetose, and we know that a certain oxidic linkage is between the first and the fourth carbon. So we're going to have 4 there, which is circled on top. Then the last sugar we have is mannose, which is running from 2, 3, 6. 2, 3, 6. So here we know that mannose is an aldose also, and it's got its oxidic linkage at carbon number 1 and between carbon number 1 and carbon number 5, but we'll put 5 here. Yes. Then now, once we are done with placing these numbers in the shells of the respective sugars, we're going to compare their numbers, like we're taking them two at a time. So we'll look at glucose and galactose. Glucose and galactose have what number missing? You look at the number they are missing. Of course, they have a 1, maybe because okay, I was thinking that they have a 1 because the 1, okay, no, this is the wrong type of thinking. No. Anyway, we'll look at the the numbers which are missing between glucose and galactose, and we're going to realize that it's 1. So we're going to put 1 in the brackets there. Then we're going to look at the number which glucose has that galactose does not have, which is the 6, and then we put them in brackets. But if we go back to our statements above, we're told that glucose was given out by an alpha glucosidase. So we're going to put the alpha there because we know that the alpha comes first. We could have put a beta, but then we know that the alpha glucosidase will give us the first sugar, which is glucose. So here glucose is dominating and we're going to have the alpha. Dali, so am I okay there, or you may come in?
Atian Dong, eh? Sorry, I was on WhatsApp. What's the query here?
I'm from explaining how the numbers 1,6 have come about there. Now, am I okay there, or you may come in, you may assist?
No, you can continue. I'll just, when you finish everything, then I'll recapitulate.
Okay, sure.
Yeah.
And then we'll move on to look at galactose and fructose. When you look at galactose and fructose, here we have galactose and fructose, we have A1. Apparently A1 is dominant. I don't know how, but then I think they'll also look at that. But then we have A1 here, and then we look at the difference in numbers here between galactose and fructose, and we realize that there is A1. The lowest number here is A1, and yeah. And then we look at what galactose has and fructose doesn't have, which is a 4. I think here we go for the lowest number, if I'm not mistaken. Then if we see the beta there, the beta is being brought about because of the beta galactosidase there. So there's something we can put in front, which is a beta, because of the presence of galactose. Then when we move on, we look at fructose and mannose. Fructose and mannose have they have 2 and 1, 3 and 3, 6 and 6. What they are missing, what both of them is missing is 4. So that's why there's a 4 in the brackets there. And then the 2 is, we're not putting 1 here because apparently mannose had a free linkage, had a free carbonyl group. Yes, it had a free carbonyl group. So we can't really put a 1 there because the one on the other side between galactose and fructose is being characterized by the fact that fructose has no free, its first carbonyl group is not free. Yes. Then when we come to naming here, here I won't put alpha or beta because, well, mannose was not released by any enzyme, so wasn't fructose. So we'll just leave it like that. Then when we're naming, we're going to have D. D is, as Delis explained last week, he talked about dextrogenes, something like that, about pouvoir optique rotatoire. That talks about their light sensitivity. So here we took this to be light sensitive, positively light sensitive. So we have D, gluc. When we're naming, we start with the first sugar we found. Okay, according to the series of the drawings. So we are going to have D-glucopyranosyl. You might be asking where pyranosyl is coming from. Well, when you look at the Haworth and the toluene, we are told that the oxide bonds between the first and the fifth carbon of a molecule is called a pyrene. Yes, a pyrene. So this is where the small pyrene there is coming from. So it's going to be glucopyrenosyl. And then we're going to put the number which is between glucose and galactose there, which is alpha, open brackets 1,6 close brackets. Then we are going to have galactopyrenosyl. Galacto, you get the prefix is characterized by the beginning of the sugar, and then the pyrenosyl is like the pyrano. Yes. Then we're going to have beta there. Again, yes, we'll have beta. So we'll have beta 1,4 with a fructofuranosyl. So we know that fructose is a cetone. And so cetone oxidic bonds are between the first and the fourth, as we stated there. So we're going to put the furano in between the suffix, which is a zyl, and the fructo, which is a prefix. So we're going to have fructofuranosyl. Then the last one, we're going to have 2,4 without beta or alpha, because in the statement above they didn't mention anything about an alpha enzyme or beta enzyme coming in. So we're going to have we're going to have pyranose. Yes, because mano from manos and pyrano from the linkage, the suffix which is OSE. Yes. If there are any questions, you can ask.
I've got a question.
Sure, Daliso.
No, it's not actually a question, but to just say, Tonga, you've really explained everything in detail. On point. On point. There's nothing like no shan. Everything has been explained. Excellent. Excellent. But another thing, please. Not that is to say, dang, because if I lied, you said there is nothing. I was just telling you what I also know. So please, also there is from what there was saying in our notes, dextrose. Please. You just say no. From the notes we learned dextrogil, furanosyl, all those things. So please, there is no shan. But otherwise, you've really explained it excellent way. Keep it up. Yeah. So I don't know if there's need for me to explain. Is there need?
Yes, there is.
Okay. So like I said, the guide here is you should, if you have your TD with you, you should check. Les réactions qui est soumise à une réaction de perméthylisation suivie d'hydrolysis acide. On obtient les dérivés méthyl suivants. D3,4,6 tétraométhylglucose, D3,4,3-triométhyl galactose, D3,6 triométhylmannose, 1,3,6 omethyl fructose. This is what we've obtained. Then I said, your guide will be, if it's a tetra, it always be at the beginning or at the end. But for a tree, for a die, it can either be in the middle. It can either be on the middle, but it can also be at the end in a case where you do not have another tetra. Like in this case, we only have one tetra, and it also justifies, or it is in line with the reactions that we had. The first one, which shows that alpha galactosidase is our starting molecule, and the second one, beta galactosidase, which is going to be our second molecule. Then the third one, après le methylhydrazine, ozazone. Then the last one, which is the methylozazone. Then the last one we stated to say, because avec liquide de phényl, le précipitate rouge, c'est-à-dire c'est une outdose. So it justifies all the reactions properly. All the reactions are proper. Now, this is now where I come in with the definition of what is the difference between fructose and all these galactose, mannose, and glucose. So I said, this is now where I say, so I said the first carbon atom of any glucid that comes from the class aldose, it will form a liaison with carbon number 1 and carbon number 5. And that liaison will be called a what?
A pyrene.
A purine. A purine. It will be called a purine. Then we said for the glucid molecules that come from the class cetose, they form a liaison at carbon number 1 and carbon number 4. What oxidic linkage is that called? What is it called? The oxidic pont. What is it called? What is it called? What is it called? At carbon number 1 and carbon number 4 for a cetone function. That is a cetose. What is it called? the
purine.
It's a furan. Then now this is now how you work out the numbers. But I was just using to my series and sequence all those things. But now here are the justifications. So we are saying the glucid or the glucose molecule for the first one, the chain is glucose, galactose, fructose, and mannose. Now we're looking for the positions in which we are going to have the glycosidic linkage. So it is found that at position 1,6, 1,4, and 2,4, this is where we have the glycosidic linkages. Now, how do they come? How do they come about? What's the how? That's the question we're supposed to answer now. So in the reactions here, we have 2,4, 2,3, 4,6 tetra or methyl. So these ones are already taken. They are already taken. Now, like we stated last time, we said they are supposed to have hydroxyl functions that are lib. Then when there is a reaction with iodine, the methyl, we are going to have the production of these oxide or ethers. You are going to have these ethers, in other words. So it means at position 2, 3, 4, and 6, you have ethers. So it means also that at position 5 and at position 1, there must be something happening. Now, for glucose to be in position number 1, it is supposed to satisfy conditions, of course. That is, 1 is supposed to be an aldehyde. It's supposed to also have a carbon number 1, which is libre, of course. Now, we know that at position 5, for us to have a cyclic hydrocarbon or a cyclic glucid, we are supposed to bond the carbon at number 5 to the carbon at number 1. We are supposed to bond the carbon at number 5 to the carbon at number 1. Now, in our case, it won't be the case that we're going to use, because it is found that at carbon number 1, there is a glycosidic linkage that is coming from the glucose molecule. Or in other words, what I'm trying to say is the glucose molecule here is not libre. Is it clear? The glucid molecule here is not libre. The glucose molecule is not libre. C'est-à-dire, the carbon number 1, which was supposed to be in the liaison avec this one to form a pont oxydique, is not libre. Then, when you go to the galactose molecule, you find that on the permethylation reaction, you have at position 3, 4, and 2, 3, and 4, the formation of ethers or methyl ethers. So it means at position 1, at position, is it position 2? No, position 5 and position 6, we still have nothing that's happening. We still have nothing happening. C'est-à-dire, at position 5, we are going to have the formation of another oxidic pont. We are going to have the formation of another oxidic pont. Now, at position number 1, that is going to also help in the formation of this oxidic pont. That is going to also help in this oxidic pont. Will appear for don't appear. It will actually, this one is going to make the oxidic pont. That is carbon number 1 and carbon number 5. They are going to make the oxidic pont, which is going to be called a purine because it is an aldose. Now, we are going to have at position number 6, which will be the only one that is going to be libre. C'est-à-dire, the galactose position number 6 is the only hydroxyl function that is labile, and it's the only one that is going to bond with this glucid molecule on the other side. So it means what you're supposed to do here is look at which positions you are having the formation of the ethers, that is position number 2, position number 3, and position number 4, d'après la réaction de perméthylisation. Same applies to glucose here. You have at position number 2, position number 3, position number 4, and position number 6. That makes the tetra. Now at position number 5, and also at position number 5, you have the formation of the oxidic linkages. At position number 4 and at position number 5, you have the formation of oxidic linkages. Now we are saying for the glucose molecule, the one here, which is supposed to also help in the formation of the glucid, the oxidic pont, is associated with the liaison glycosidique, c'est-à-dire the carbonyl function of this glucose molecule is not libre. Why? Because carbon number 1 has been engaged in a liaison. It has been engaged in a liaison. But now, because it has been engaged in a liaison, it means the carbonyl function is not libre. Then for galactose, same applies to galactose. At position number 2, position number 3, and position number 4, you have the formation of ethers. At position number 2, number 3, number 4, we have the formation of ethers. It's not like I'm just saying this thing. It's the reactions that you can see on the bottom there. That is 2, that's 2, 3, 4, 3 or methyl galactose. So at position 2, position 3, and position 4, you have the formation of these ethers. Now we are saying at position 1 and position 5, we are supposed to have the formation of this oxidic pont. We are supposed to have the formation of this oxidic pont. Now, the only one that's going to remain now, that is going to be libre with a hydroxyl, is position number 6. Therefore, position number 1 from the glucose molecule and position number 6, which is the only one that is libre from the galactose molecule, is going to result in the formation of this glycosidic liaison. It's going to lead to the formation of this glycosidic liaison. Take note, the oxidic pont that is supposed to be formed by glucose here in this molecule here, at position 1 and 5, is associated with the glycosidic liaison. C'est-à-dire, the glucose molecule here is not libre. It is engaged in a glycosidic liaison. Is it clear? Is it clear? Alhamdulillah. Same applies to the next molecule. Same applies to the next molecule. Now, for the next molecule, we are saying, for the next molecule, we are saying, okay, this is a galactose molecule. It is a galactose molecule. Now, please, I beg your pardon. I screwed up here. So we are saying at position number 1, same applies to the galactose molecule. It is not libre as well. At position number 1, the galactose molecule is not libre. So the position number 1 for the galactose molecule, being an aldehyde, isn't free. So it is going to also be involved in the glycosidic liaison. Now, when you go on the other side here, because how these numbers come about is you get one from the one on your left, and you also get the other liaison from the one on your right. Same applies to this one and this one, just like that. That's how you get your liaison, the positions of which one is at which position. So the position 1 here that you're seeing, the first one here is for the galactose, and the position 4 is for the fructose. So now how does the 1 and the 4 come in? So we are saying at position 1, because this galactose molecule is not in a free carbonyl function, it's going to be engaged in a liaison. Now, the fructose molecule in our case is supposed to form a linkage at position 1 and at position 4. At position 1 and at position 4 for the oxidic linkage. oxidic linkage. Now, it so happens that at position number 2, which is where the aldehyde function, the ceton function is defined for fructose. At position number 2, it is defined that this is a ceton or a cetose. We are going to have the 2 involved in another liaison with another molecule. So it leaves us with a 1, and the 4 here will be found also in a oxidic liaison, which is going to be called a furan. It will be called a furan because this is a derivative of the ceton function. It is called a cetose and forms what you are calling a furan oxidic linkage. So at position number 4, it is going to form a furan oxidic liaison. Theta D, we are only going to have how many of these positions remaining? We're going to have, is it 3? We're going to have 6, 3. There's no, is that 2 here? No, there's no 2. So we're only having, what do you call them? The ethers. Ethers are formed at position 1, at position 2, 3, at position 6. Then we also have another case. We know that the fructose molecule, let me just repeat this. We are saying at position 1, we have the formation of an ether. You can look at your reactions below there. You have the formation of an ether. At position 3, we have another ether. At position 6, we have another ether. So at position 1, position 3, and position 6, we have another ether. Now, this 4 here is not correct. So 1, 3, and 4 are the positions of the ethers. Now, we are saying 4 is found in an oxidic liaison. It's found in an oxidic liaison. Now, this, like I'm saying, this 4 is not supposed to be here. We're supposed to have a 5 here, so that it shows that at position number 4, we have the formation of the oxidic liaison. Then the only position which is remaining, that is 5, is going to be involved in a liaison with galactose, so that we have a glycosidic bond at the end of the day. Because we are saying at position number 2, it is not libre, it will be involved in a ceton liaison, which will be called a glycosidic liaison at the end of the day if it forms a bond with mannose. Then we are also saying that at position 1, at position 3, and at position 6, we have the formation of 3 different ethers d'après réaction de péméthylisation. D'après réaction de péméthylisation. And at position number 4, we have the formation of an oxidic bond. Then the only position that is going to remain will be 5. C'est-à-dire, it will be the 5 that is going to make the liaison with 1 here, so that we are going to have a glycosidic bond. So that we have a glycosidic bond. Then, since we are saying position number 2 isn't libre, we are going to have position 2, that is for mannose, position 3, and position 6. These are going to form ethers. This is 1 ether, the second and the third ether. We're going to have the formation of 3 different ethers. And we are saying also that at position number 1, we are supposed to have a carbonyl that's going to be libre, so that the first reaction avec liquid féminin, we are going to have the formation of a red precipitate. We are supposed to have a carbonyl function at position number 1 that is going to be libre, so that we have the formation of the rouge precipitate. Now, which is this case, the carbon that is number 1 is libre. Then it remains now with carbon number 4. That is going to be the only one that's going to remain, and it will be the only one that's going to form the liaison with fructose. Then we are going to now have this as our nomenclature. So I'll repeat. So we are saying the chain is made up of glucose, galactose, fructose, and mannose. So this molecule was subjected to different reactions, but now the reaction that we're considering most now is la réaction de péméthylisation. So we are also saying or stating to say the first one, which is 2, 3, 4, 6 tetra or methyl glucose. So there are how many ethers that are formed here? We said, first of all, la réaction de péméthylisation is a reaction that is used to determine which hydroxyl functions are free, so that we have the formation of ethers of glucides. We have ethers of glucides. So now it has been found that at position number 6, position number 6, position number 4, position number 2, position number 3, these things are found on your TD, please. They're found on your TD. Position number 2, position number 3, position number 4, position number 5, we have what we are calling a tetramethyl glucose. So these are ethers. So the only positions that are going to remain is position 1 and 5. Now we are saying position 5 is supposed to be found in an oxidic liaison. The oxidic liaison is what we are calling the purine, because it is formed from an aldose. It is formed from an aldose. In our case, glucose is our aldose. So if position 5 is already occupied, that leaves us with position 1, which also implies that the carbon number 1, which is this one here, the one that has been involved in a liaison, the glycosidic liaison, is not libre. It is not libre. It is not libre. Then when you go to the other side, that is the galactose molecule. Now we're looking for the carbon atom that is also involved in the glycosidic liaison. Now we find out that d'après la réaction de péméthylisation, we have at position number 2, position number 3, and position number 4, the formation of 3 methyl ethers, d'après la réaction de péméthylisation. So we are also stating to say that at carbon number 1 for the galactose molecule also involved in another liaison, c'est-à-dire ce n'est pas libre. Then position number 5 is also involved in an oxidic liaison, which is going to be called purine, because we have an aldose, and galactose is an aldose. So position number 5 is occupied in an oxidic liaison, so we are going to have the formation of a purine. Therefore, it leaves us with position number 6, which is going to be the only one. Position number 6, that is going to be libre with a hydroxyl function, and there is going to be the formation of a glycosidic liaison, that is at position number 1 from the glucose molecule, and position number 6 from the galactose molecule. Then we forge ahead. So we are saying the galactose molecule at position number 1 is not libre, ce n'est pas libre. Then we are also stating to say that at position number 1, position number 3, and position number 6, we have the formation of 3 ethers d'après la réaction de péméthylisation. D'après la réaction de péméthylisation, which is the reaction of methyl diode avec une glucide to form an ether. So the ether is formed only when the hydroxyl functions are libre. So please take note. These other reactions, that is oxidation of transition metals, oxidation of, iodine and bromine, and which one is it? Reaction de quoi? There's another reaction. There should be 3 reactions. They all look at the first carbon atom and it being an aldose and all those things. But la réaction de péméthylisation, it is always the hydroxyl, either position number 1, position number 2, 3, 4, ends in the suite. So la réaction de péméthylisation only looks for free hydroxyl functions. Free hydroxyl functions. Now in this case, we have at position 1, position 3, and position 6, which are the ethers that have been formed from fructose. C'est-à-dire, position 4 is also engaged in another liaison, which is going to be called a furane, because fructose is a cetose. So the cetose form an oxidic bond at position number 1 and at position number 4. Now the 4 here has been engaged in a liaison. It has been engaged in a liaison, which is going to be called a furane. That leaves us with only one position, which is going to be position 5. Now, like I said, it wasn't supposed to be 4 here. It was supposed to be 5, not 4. It's supposed to be 5, not 5. Because if you put a 4 here, that disqualifies this molecule here. The molecule here is a fructose, it is a setose, and forms a furane. And the furane, we stated to say, the oxidic bond is found at position number 4. It is found at position number 4. So here, please, if you're writing this, it's supposed to be 1, 5. 1, 5, because it is only at position number 5 that you have no formation of an ether. It's only at position number 5 where you have no formation of an ether. Then we go to the last part, which we are saying the fructose molecule is not labeled as well. Why? Because at position number 2, where we have the carbonyl function, where it is defined, because it is a cetone, it is defined that at the second carbon atom, it is engaged in a glycosidic liaison. It is engaged in a glycosidic liaison. The fructose molecule is a cetone, and at position number 2, we stated to say that the fructose molecule being a cetone, at position number 2, this is where the function is defined. That is for the cetone carbonyls. So we are saying at position number 2, ce n'est pas libre. C'est-à-dire, we are going to go on the other side. Now we are looking for another carbon atom that is free to be engaged with a liaison or a bond with fructose. Now it is found that at position 2, position 3, and position 6, we have the formation of ethers, which you can see from your polycopy or bien your TD. Says position number 2, number 3, and number 4, you have the formation of ethers d'après la réaction de perméthylisation. Now, mannose is an aldehyde, and it falls under the class of aldose. Then it also forms a purane oxidic bond at position number 1 and position number 5. This is now where you have the position number 5. This is where we have the position number 5. So the only one that's going to remain now is going to be position number 1 and position number 4. Now we are saying for everything to flow, for every reaction that we have here, A through F to flow, we are supposed to have a carbonyl function that is supposed to be an aldehyde, which is true. This is an aldehyde. It is true. It's an aldehyde. And the carbon number 1 is supposed to be libre, so that we have reaction number 1, so that we have also reaction number F. We also have reaction number F, even though we don't need the carbonyl function on those 6. So basically, so that we have reaction number 1, which is the formation of a red precipitate. So it is at carbon number 4 that we are going to engage fructose with in the glycosidic liaison. It is going to be position number 4, we are going to engage in the fructose liaison. Why? Because at position number 1, we are stating to say that when this molecule or the triholoside reacts with, is it liquid de fémine, we are supposed to have a red brick. Is it the brick rouge or bien rouge brick that's going to be produced? So at the end of the day, our molecule will be called a D. So this is what I forgot to mention. So all D glucose or glucid molecules are natural. They are natural, like they are found in nature. Then the L's ones, maybe, is it produced by man? So it's going to be D-glucofuranosyl alpha 1, 6, galactofuranosyl 1, 5, not 4, A5, beta 1, 5, fructofuranosyl 2, 4, manopuranose. It will be D-galactofuranosyl alpha 1, 6, galactofuranosyl beta 1, 5, fructofuranosyl D4, manopuranose. So, like Taonga stated to say, because there is no enzyme that's giving the direction in which fructose and mannose were hydrolyzed, we are not including the alpha and the beta. And not only that, the alpha, the other part, now we're done. The other part is, there's what you call alpha and beta. I explained this. Alpha is the orientation of the hydroxyl functions, either upwards or downwards. Same applies to the beta. So if you have a hydroxyl function for the glucose molecule or a glucid facing upwards, you call it an alpha orientation. If you have one that is facing up and down, we call it a beta orientation. But if there's any case of confusion, maybe I might have confused them. That is, in any case, it has been long when I did this. So in a case where there might be confusion of the two, but one is supposed to be oriented facing up and the other one is supposed to be oriented facing down. That is in the case of the hydroxyl functions. Are there any questions? Are there any questions?
I don't think so.
On se verra, Inch'Allah, demain pour la chimie organique. S'il vous plaît, préparez-vous parce que demain, ça sera chaud.
Bye, Dalisa.
Bye.
Before we go, I have a question. When are we going to do the next two?
Yeah. I think he's gone.
La prochaine fois. Inch'Allah.